Okay, thank you. Okay, so that's good afternoon, good morning, good evening, good night, wherever you are. And I guess sort of welcome to the last week of the semester. So there's 2 more class meetings today, which we're going to be talking about Blockstack. And on the first day, we get a report from the different projects, from a number of the project groups in 6824. And so today is basically the last paper discussion day. And so the topic is, the system that we assigned for, what I assigned for reading was is Blockstack. And really what Blockstack represents is an approach to building decentralized applications. And with decentralized, what we mean here is that unlike in centralized websites, the sort of website owns the data. In decentralized application, the system is set up in a way that the users actually keep control over the data and not the website. And so this forms sort of a trend in the last, this sort of the final lecture in this sort of series of 3 lectures on decentralized distributed systems. We talked about logs and signing, or sign logs as a way of constructing these decentralized storage systems. We saw Bitcoin to see as an example of how you can achieve consensus in decentralized systems with entrusted participants or Byzantine participants. And so today we're sort of taking one more step up and actually look at like how you can actually even build complete applications other than just cryptocurrency applications. And decentralized applications have a long history. In the early 2000s, late 90s, there was a lot of to do around peer-to-peer applications, which had a decentralized architecture like Napster. More recently, you're probably familiar with Keybase, which has a decentralized design, or Solid, and of course Blockstack. And so there's quite a bit of activity in this space of decentralized applications. The Blockstack is interesting from the perspective of actually running decentralized applications, but also is an example of sort of a non-currency use or non-money use of Bitcoin, of the blockchain, the Bitcoin blockchain. And we'll see, there are a number of aspects that are interesting in Blockstack, but the key thing that the sort of paper focuses on is actually naming, how to sort of build a distributed, decentralized naming system. And of course, naming systems are widely used. If you think of DNS, think about Kerberos. There's tons and tons of different naming systems out there, widely used. And this is just a different design, and where the most interesting part of it again is it's decentralized. Now, this lecture is a little bit different than sort of the preceding lectures, or many of the preceding lectures. Many of the preceding lectures I sort of have the flavor, well, here's a hard technical problem, here's the solution to solve that particular problem. And here we're in a slightly sort of different position. There's a hard technical problem, and we have to build decentralized applications. But it's not, 100% clear that it's exactly, the right thing to do to build decentralized applications, and it's extremely intriguing. And it's also not clear that like Blockstack is just the right solution to do so. And so it's much more experimental. Blockstack does actually have a user community, but it's not like yet an overwhelming success and a demonstration that this is sort of the right way to go. So in that sense, this paper in some sense is more thought-provoking than giving actually a definite answer to a particular technical problem. And so in some ways, this is a more of a topic that is sort of lends itself to a lot of debate about the different views on this kind of design. And so during lecture, if we get to it would be perfectly fine actually to have quite a bit of discussion on different aspects, and I don't think there's going to be one right answer. And so anytime you have a question about or want to sort of argue about a particular aspect of sort of these decentralized app designs, speak up. Okay, So maybe before talking about decentralized apps, just like quickly revisit, actually what's sort of the common paradigm to actually build websites or build web applications, right? And that's really using centralized websites. The site itself might be distributed across multiple data centers across the world, but the architecture or the design of the site is centralized, where we have, here's your sort of your typical website. It has some applications and code, whether Gmail, whatever, Twitter, Facebook, and that operates on a database that contains users' data. And we might actually have different users interacting, with the sitting behind a web browser, and user 1, user 2. They interact, through the application with the website. They create data. The data is stored in the database. Other users may view the data, and the application displays basically that data to inside of the web browser. And the data might be blog posts, tweets, Piazza posts, photos, perhaps even more sort of sensitive, medical records, etc. And basically, the application we're running on the site, transforms that data from all the different users into something that's interesting to look at, where basically integrating, for example, the timeline of many users into a single timeline presented to the user, organizing the tweets, doing ups and down votes, et cetera, et cetera. And one sort of distinguishing feature of this sort of design is that the application and the data are sort of bundled. They're under the control of the application site, whether it's Facebook, Twitter, Google, or any website. And really, the interface between the user, or sort of the dividing line between the user and the website, is basically HTML or the UI. The application basically computes whatever the user is going to see, and that's going to be displayed inside of the browser. Of course, the application might actually run inside of the browser, like JavaScript, but that's actually not really pertinent to this particular discussion. It's still, the application is under control of the website. The programmers of the website write the application, and the application basically manipulates the DOM fields from inside of the web browser. And so, from the user point of view, the interaction, the interface, between the dividing interface between the website and the browser is still sort of HTML. And so this this design clearly is overwhelmingly successful. Most websites that you probably, actually probably all of the websites you probably use are sort of following this particular design. And one reason for this very successful design, as we'll talk a little bit more later, is because of the tight integration between the application and the data from the different users. So the application has easy access to all the users' data from different users, and integrated them in creative and interesting ways. But there are it's not completely perfect, this design, and so there's sort of things that you might wish could be slightly better. And in some sense, decentralized applications is a response to those sort of things that are might be not 100% desirable. And so, for one, here's a very simple observation: you can really not create another application. So the site decides actually how the app looks like, and that's the UI you're going to get, and which is sort of very different than let's say you're running applications on your laptop. For example, you want to modify and edit a text file. Well, you get to choose which browser or editor you're going to use. Whether you're going to use Emacs, Vim. You can have whole kinds of culture wars about which one is better than the other. But you get an option. You get to choose which one you want to use. And in this case, that's just not the case. If you're using Gmail, Gmail is not the best example, but Twitter, Twitter is going to decide actually how the application is going to look like. The reason why Gmail might not be the best example is because you can actually download your email maybe through IMAP and then run your own email program. But for many websites, the user and the application data are very controlled, and you have no control over it. The website may change the rules on who can see and what data. and might actually do it without really telling you. And so you don't really have full control over actually who sees your data. Furthermore, the website actually might use it, your data to generate revenue, whatever, to decide which ads actually to display, and basically snooping over your data, right? Or in the worst case, maybe a bad employee actually just snoops over your data. And that's really sort of outside of your control. There's nothing you can do about it. You give the website the data, that's theirs now. And so this is the sort of pain points. It makes people wonder, is there a way of designing systems that really don't follow this paradigm, but follow this paradigm of decentralized applications. And so in this world view, sort of whenever we still have our internet, the cloud, but we have storage providers. And your storage providers are basically nothing really sophisticated, where they don't really run app code. They just purely provide storage, ways of, maybe it's like your Google Drive or whatever, or Amazon S3. But basically, they're sort of dumb, bit holders. The data maybe, the user probably wants to encrypt the data. But basically, what the real goal here is that the user decides, which storage, where the data lives, and it keeps under the control of the user. So whatever, storage provider S3 might have, users one data. The other storage provider might actually have user two's data, or stores, data on behalf of user two. User two and users S3 may actually encrypt it, so that the storage provider can actually not read it, and control like who can actually decrypt the data. And then the applications really are in the control of the user themselves. And so we have a user here, user one's workstation or laptop, runs an application, and here's U2. There's also another application, maybe actually looking at maybe at the same data, but like a slightly different version of the application, whatever, one photo viewer and another photo viewer. And basically to construct, the sort of what is actually shown to the user, the application fetches, data, from different users. So for example, if U2 shared the photos with U1, then the application sort of integrates the photos of U1 and U2 by extracting or retrieving the photos from the different storage providers. And here, really, what the sort of dividing line is between users and the dividing line is really this. There's sort of a dividing line between the application and the storage. And sort of there's a storage API that has to sort of be uniform, because many different applications are going to use the same storage IDFI. Maybe this application creates to-do lists. Maybe it's a photo list, maybe it's a Twitter clone that basically retrieves the tweets from different users and integrates them and presents them to the user. And it's really that sort of single storage API, or that actually provides the dividing line between the applications and the data. And of course, that source API has to be quite general purpose, support multiple applications, but also has to allow sharing between different users and different applications, modulo the permissions. Right? And so, let's say you wanted to build sort of a shared, to-do list. Then between user one and user two, then let's look at this from the perspective of user one. Probably there would be some operation or some sharing operation between user two and user one, saying like, yeah, here's the names of my to-do list, and user one can then download the user two's to-do list. Maybe check the signature on the file to just verify that data was indeed written by user two. And then integrate that with its own to-do list, and present to user one a shared to-do list that contains both user ones and user twos to-do items. So that's sort of the general view of actually building these or sort of this decentralized architecture for applications. Any questions so far? Okay, so this so far hopefully we've seen that this addresses one of the sort of the major pain points for the centralized approach. That basically the users stay in control of their data. It's not owned by a particular site anymore, and the users decide who or which applications and who actually can get access to data. And that's a desirable property. But this whole design is also with its set of challenges. So let me lay out some of them, and then we'll focus on a few of them in the context of Blockstack. And so there's sort of two, I think, broad categories of challenges. One sort of on the business side, what is the revenue model? What will get these applications actually being adopted, and pay people money to actually develop the applications, and so that they actually become really good, and people are excited about using them. Not really going to kind of talk about that at all, but instead, I want to mostly focus on the technical challenges. And there's several of them. One is, so if we go back to this sort of picture here before, the storage API is sort of the key interface, and the interface has to be minimal. It has to be general purpose enough, but typically it's actually it's not the same thing as the API that basically sits here, between the application and the database. Let's do that. Hold on a second. Okay, hopefully everybody can see the screen, the boards again. Good. So there's a couple of technical challenges. What I was going to point out is that storage API is typically not as powerful, or that file system API is not as powerful as SQL. And furthermore, not all the data, sort of all the users is like handy in a single place that you can run, arbitrary queries on to integrate it in, whatever application-specific manners. So that's sort of a challenge. That sort of applications really rely on the power of being able to run arbitrary queries over all the users' data. That is in a decentralized application a little bit harder to achieve because the data is spread out over maybe different storage servers. There's also features that might be harder to implement. Like, for example, if you want to implement eBay, then users have to submit sort of bits, but we don't disclose those bits immediately. So there has to be some trusted aspect to it that actually integrates these bits and then decides actually who's the winner, without disclosing those bits beforehand. Similarly, there's a sort of challenges around management. Typically, these decentralized applications, involve crypto keys, and so there has to be sort of that's often an Achilles heel. Some user loses their private key, and then you can't use you can't get to your data anymore, or somebody actually steals your private key, and then they can get at your data. So there's a sort of a series of sort of technical challenge, to make this actually really work. And one of them, the remaining one, which is really sort of mostly the topic of this lecture, is naming. And sort of these broad set of challenges are basically, I think, challenges for any sort of decentralized application infrastructure, and certainly also in the context of Blockstack. But in the case of Blockstack, we're going to mostly, we'll see actually the importance of names and why naming actually is a challenge. Okay, so before continue, I just want to stop here for a second and sort of give people time to ask any questions to sort of contrasting sort of these two different ways of building applications, whether it's centralized, as in the sort of the traditional model that we're probably all familiar with, or this decentralized model.
So what's the challenge exactly with bids?
So which challenge?
With bids?
Oh, you need an application needs to have access to the user bits, but shouldn't disclose them, right, to other applications. And so that means that the application, like I'm U1, I'm submitting a bit, I get U2's bit, but my application shouldn't really disclose U2's bit immediately to me because that wouldn't be fair. And so how would you do that? So you need some sort of form of a trusted party or whatever, some protocol that actually makes that happen.
Thank you.
If the application runs on your workstation, you can modify the application, correct?
Sorry, in the previous slide, I think you mentioned also app one being different from like the two apps being different. What do you mean exactly?
Well, okay, just to make the analogies very crisp, this could be Vim, and this could be Emacs. And U1 and U2 get to decide which application they're going to use to actually modify their data, correct? And today in the sort of centralized model, it's not really possible. You can't have basically two Twitter apps, where you were like one way of interacting with the Twitter app and somebody else likes to do it in a different way. Let's just do a Twitter app.
I see. Thank you.
I had a question just about like the design of the decentralized app model. Is it necessary for the app to be like on the client side, or could it could you have like these decentralized apps on the internet side?
You could have in principle on the internet side. The key issue, and it doesn't really have to run on the user's workstation. It can run anywhere, but it is under the user's control. Of course, you have somebody who writes it. But the user gets to decide which app to run over what data.
Right. So the important thing here is that the user chooses the app, and
Yep.
Importantly, the app has access to any storage provider, right?
Yep.
Thanks.
Okay. Any other questions? Okay, so names. So, and this is getting a little bit more into Blockstack. And then let me sort of lay out like the role the names play. First of all, you have a to-do list and you want to share that with somebody else. You're going to have to be able to name that user from whom you're sharing with. And so there's a sort of mapping from name to user. That's an important role. There's a mapping sort of from name to location of data. So if my to-do list app, I share the to-do list of user one with user two, and then I want to actually retrieve, user one wants to retrieve user two's data. There needs to be a way of actually naming user two's to-do list and actually retrieving it. And then there's a name to public key mapping. When I do successfully retrieve user two's data, I probably want to verify that it actually was written by user two, and so I'll probably use user two's public key to verify the integrity of the data retrieved, because the storage providers might be can then be untrusted, but that requires that I can establish what actually user two public key is in a reliable manner. And so you should think about it like in every step of these decentralized applications, a name plays a crucial role. And and the common name given in particular for these mappings from names to keys, which is a crucial piece, is typically called a public key infrastructure. And that is, building actually any public key infrastructure is quite challenging. You might be familiar with like DNSSEC, is a particular way. Of course, the World Wide Web has with certificates has a whole public key infrastructure. Kerberos is an example of public key infrastructure. And in some ways, what this paper sets out to do is just build yet another public key infrastructure that is completely decentralized. And that's sort of the key aspect, of this. What's interesting about this naming scheme in Blockstack, that's actually provides a decentralized public key infrastructure. Let me try to explain a little bit why this is challenging. So the paper refers to this in a couple places. And it says, like, there's three aspects that you want. If you want sort of a general purpose naming infrastructure, you want to be able to have unique names, to have a unique name for every user, so that you can identify, the particular John or the particular Joe you're talking about. You want human readable names. So that's easy to remember. And then in this case, what Blockstack also wants is decentralized. And the paper more sort of makes a point that it's easy to get two of the three, but it's very difficult to get all three of them. And maybe let's look at a couple naming systems to see which two they do get. So let's think about like email addresses. So let me. Okay, email addresses, are they unique names?
Yes.
Yep. Are they human readable?
Yep.
Yes.
Are they decentralized?
No.
No. So these just get two of these guys, correct? But not the first one. How about random public keys? Or maybe like if the paper uses hashes of the file contents to actually get a name, correct? For a thing. So basically, okay, so random public keys. Actually, maybe just public keys, forget the random, but presumably they're random. So public keys, are they unique?
Yep.
Yeah.
Yep. Are they human readable?
No.
No. Are they decentralized?
Yes.
Yeah, you can generate them, with high probability in a unique manner, completely decentralized, correct? So in fact, you should have done that more in lab 3 with these clerk IDs. So here we get like, again, two of the three, but not the human readable one. Let's see, can we actually get human readable and decentralized? Can you think of an example?
Isn't it like peer-to-peer file sharing?
Yeah,
like
it's not what I was.
Not unique, the files, but they're human readable and decentralized.
Yeah, no, think simpler. Think about your phone. The example for me always is a good one. It's like your contact list. Yeah, the names in your contact list are human readable, decentralized. You can have John, in the entry for John 1 phone number, and I can have another phone number for my John entry. They're probably different people, but I can pick the names in a decentralized manner, and they're certainly human readable. Are they unique? No, right? This is like you have your list of names, I have my list of names, and they may actually overlap and still talk about different people. So here's sort of what the paper is trying to get at that actually getting 2 out of the 3 is quite common or very easy, but actually getting all 3 of them is hard. And the paper says, like, well, we actually we achieve all 3 of them. And we get the unique names, we get human readable and decentralized, right? And in the way, in some ways, they get this is to basically exploit the blockchain. And so so Blockstack's approach. And really, to be fair, it's really not Blockstack's approach. It's really Namecoin's approach that they sort of adopted. But the basic idea is very simple. We're going to take advantage of the existence of the Bitcoin Blockstack, or the Bitcoin blockchain, and of course you could use any other blockchain, but just for concreteness, we're going to think about the Bitcoin one. And so here we got our chain, of transactions that sit in Bitcoin, and grows over time. Miners add new transactions, and the way we're going to basically create a naming system is we're going to just post transactions that are of different type that basically claim a name. And so, for example, we might actually have sort of these special transactions. Because every transaction actually turns out in Bitcoin has a metadata field, and you can basically stick anything in the metadata field you want. And so what we're going to stick in there is a name record. So we're going to have some transaction, and then we're going to stick a name record in there. We'll see a little in a second what exactly the details of this name record is. But in the case of Blockstack, it's basically a name like 6824. And then, maybe, as we'll see later, a hash of a zone file. And the basic rule in this scheme is going to be that the first one, the first user, the first name record basically wins. Right, so there might be a second, somebody else creates the name 6824 later. And not because the 6.6824 shows up later in the Bitcoin blockchain, we're going to basically ignore that one, and only consider that the valid name record for 6824, right? And this completely plays off on the fact that basically the blockchain is a log of all the operations ever happened. They're in order, there's consensus in what order they happened. And so from that, we can basically construct, if you will, like a database with all the names in the world. We just go through the blockchain from the beginning of time, find all the valid transactions, named transactions, and use that to construct a database with all the valid names. And in some ways, a number of people sort of pointed this out, like, isn't this exactly, what we've been doing like Lab3, where, we have a log, like Raft, provides a log, we stick operations in the log, we run, the operations, and that constructs, a state, where the state in this case would be a naming database. And there's, I think it's exactly in that kind of style. In the same idea, except there's small differences here, correct? We're not using Graph to get consensus. We're using Bitcoin or Nakamoto to get the Nakamoto consensus to actually achieve one single blockchain. But in spirit, yes, it's very similar. Okay. So let's think a little bit about it. Our 3 properties. First of all, do we get unique names?
Yes.
Yes.
Yeah, we get unique names, correct? Because the first one wins. Is it decentralized?
Yes.
Yeah, it's decentralized, by sort of virtue of Bitcoin, right? And the consensus and the log basically makes it sure that we can actually identify what the first name is so that we can actually pick a unique name. Is it human readable?
Can be.
Can be, yeah, exactly. Okay. Certainly my string 6824 is hopefully human readable. Okay, so it seems like, sort of on the first broad, sweep where, it looks like indeed, we got the three properties, right? Got the human readable, we got the uniqueness, and we got the decentralized one. And I think a really named coin was sort of the first naming system demonstrated that could be achieved in this way. Now, it's not completely perfect, right? Like, for example, even though we got sort of unique names and they're human readable, we don't really know like what 6824 really means, correct? I don't know if like you see 6824, what does 6824 refer to? Is it like a part number, or is it a class number, or anything? We don't really know like how to interpret names, but they're still human readable. So it's not completely perfect. It's not like identifying uniquely some user in the world, right? Or and even like whatever you write down cashew, that doesn't really uniquely identify one person, right? So whenever you see a name here, there's sort of still the issue of like who it actually really is. And also there's sort of a similar, related issue why it's not completely perfect, which is like, how do you find somebody's name? And how do you find actually, whatever Cashew's name, or and how do you find that? How do you know which record actually goes with which particular user? So, although the system is quite cool because it has sort of these decentralized uniqueness and human readable aspects to it, it's not completely perfect. And these are generally issues with general naming systems, but certainly true here too. And so it's not the case that we sort of solved all naming problems in one single swoop. We do have a good standing position to work with, but it's not it's a complete 100% hit.
Right, so
Okay. Yeah.
just a question. So Namecoin, all they did was add essentially this like record to the like transaction.
Well, Namecoin did a little bit more than that, correct? They run their own blockchain, independent of Bitcoin, and use that blockchain purely for naming. And they had also a bunch of rules about like how much money, how many name coins you have to pay to get a particular name, and there's all kinds of other sort of extensions that I haven't really discussed yet or mentioned, but they sort of followed this particular approach, and were the first sort of to do so. And the many pragmatic issues, right, that the paper touches on, and I haven't mentioned it all yet. Any other questions? Okay, so let's actually dive in a little bit on the sort of the practical issues, although there's a slightly different nature than the ones we just talked about. It really is about how to actually implement decentralized apps and a naming system by leveraging Bitcoin. And there are a bunch of very sort of just pragmatic issues. There's limits on the amount of data you can put in on data size in a transaction. So although maybe it's perfectly fine to have sort of a name value binding into a Bitcoin transaction, we can't put like our to-do list inside of the transaction. And so we got to have some plan for actually how that part is going to work out. It has slow writes. So we know from the last lecture, it takes a while for writes actually or transactions to propagate. and before they considered to be really stable and cannot be forked off anymore. We might be talking about like 4, 5, 6 blocks later in the chain, and your block is 10 minutes, so an hour later, right? And so this is really not so cool if we stick our to-do list inside of the blockchain too, because I will modify my to-do list, like an hour later, maybe actually observe it. So that seems not so good. And if we want to go to more aggressive applications where like there's much more data that's being manipulated, we certainly a problem. And similarly, in addition to slow writes, there's also low throughput or low bandwidth. The numerator, there's only a few transactions per second, correct? So we're going to do a lot of writes, to the file. Many times we were running the file operations through the blockchain. So clearly, we got to be a little bit, if we want to really build a general purpose infrastructure for decentralized applications, there needs to be a more complete story that actually allows us to get like fast writes, high bandwidth writes, and gets us around and basically not run everything through the blockchain. The paper also talks about one other final problem: the ledger, the ever-growing ledger. And we're not actually spend much time talking about that at all. But that's clearly also an issue. If you wanted to, they report in the paper, so we're going to boot up a Blockstack node. If you do it sort of in the traditional sort of Bitcoin style, where you're going to run through all the transactions one by one, that will take a while before you actually have built up your complete naming record. And particularly in the case of Blockstack, it's a little bit annoying because a lot of the transactions that are in the blockchain are completely irrelevant to Blockstack. Right? There are whatever transactions for completely some different purpose and have nothing to do with the Blockstack approach. But Blockstack, if you really literally were using the Bitcoin blockchain as your fundamental thing, you would have to go through and interpret any of them and see which ones actually you need to apply. Okay, so we're going to focus more on sort of these first couple challenges, which is like, basically what we want to do is like minimize the use of the blockchain so that we can actually get high performance writes or a decent bandwidth. Does that make sense? Good, and that sort of gets us to the core of the paper, which is like we'll pull up that diagram so that we can look at it. And that's basically this diagram. And that sort of describes the general approach that the paper takes to address the challenges that I just laid out on the previous board. Okay, so this is a complicated picture, and so let's go sort of layer by layer and try to understand actually how things work. So at the bottom, is the Bitcoin chain. And in the Bitcoin chain, there are lots and lots of transactions, and many of these transactions have absolutely nothing to do with Blockstack. Let's write down Blockstack here. And the Blockstack transactions are sort of sitting in particular blocks in the blockchain. And then there's sort of the second layer, which is really the Blockstack nodes that basically read all these transactions, fish out the ones that are actually related to Blockstack, interpret those operations, and build up a Blockstack database with names to what turns out to be zone file hashes. So we look at these operations, what is in there. So in every Bitcoin transaction, as I mentioned earlier, you can have some metadata that sits in what's called the op_return field. And in that op_return field, there is basically a name, say X, plus the hash of a zone file. And that's sort of the binding that sits in Bitcoin, and that basically Blockstack uses Bitcoin to basically make that binding from name to a zone file unique and in a decentralized manner. So as you know, like in Lab3 or in any other sort of logging system, these Blockstack nodes interpret these particular name transactions, look at the op field, see that this op field is, for example, to create a particular name, and basically store it in the database the binding from name X to the hash of the zone file. And once in a while, as we'll see in a second, a user may want to update the zone file, and so you might see multiple transactions for the same user updating basically the hash of the zone file. Now, of course, we want to minimize these changes, because every change to the would require a modification or posting a Bitcoin transaction, and for the many reasons that are on the previous slide, that's slow, so we like to try to avoid it. Furthermore, it will cost a little bit of money, because these transactions actually need to be processed. And so, so the basic plan. So this node layer, the virtual chain layer, basically builds this database of mappings from name to hash zone file, and of course also filters out all the transactions that are invalid, or like new access that are being created after the first one, and then using the hash of the zone file, which we got, it locates an application can locate the zone file, and the zone file can come up from anywhere. And because we have the hash of the zone file, when we retrieve a file that claims to be the zone file, we can recompute the hash. If the hash is identical to the one that we got sort of through indirectly through Bitcoin, then we know for sure that that is the zone file that goes with X. And so, okay, what is then in the zone files? Well, in the zone file is sort of yet another table, if you will, of mapping names to URIs. So, for example, you might have a zone file which has, like maybe for the to-do app, has an entry to do, and that points to a URI where actually the data is located for the to-do list. And there's sort of two types of zone files. One is what they call immutable, and one is the mutable. The mutable ones have a URI plus a public key. So, and this is public key is the key to actually validate whether the file was written by the user X. So basically, the user X publishes through the zone file a public key for him or herself, and later on, when user 2 wants to look up user X, it gets the hash of the zone file. The hash finds the zone file, double checks that the zone file hashes to the right value, looks inside the zone file, finds the public key of X, and the URI for the to-do file, uses the URI to fetch the actual to-do file, check the signature on the retrieved file with the public key, and if it all checks out, then basically user 2 knows, okay, I got user X zone file. And then it might be also like other names in this zone file, like whatever, users 2 X's tweets, etc., timeline, whatever. For every application, there's probably an entry, and probably the applications sort of agree on what name to use for a particular application.
So don't we lose the data immutability guarantees where it's possible this data could be deleted and then you wouldn't have the hash and the data could just be lost?
So you mean like the zone file could get lost?
Right, like with the chain, you can't lose data because it'll be replicated in enough places, but here that's not, you don't have that guarantee, right?
Good. So it's so it turns out the zone file is also replicated widely on basically there's a core set of Blockstack nodes that all replicate the zone files of everybody. And then apparently the zone files are reasonably small, like 4 kilobyte or something in that order, and so they can be replicated everywhere. Okay. Then for the to-do list, the to-do file, the URI, the basic idea is that you might store the same data or at multiple providers. So, for example, you might want to have you replicate it at S3, and maybe you also stick it in Google Drive. And one reason that actually Blockstack has a storage service is not because actually they store the data, but basically you provide a uniform API to all these different storage providers. Okay, so does that make sense? Okay, so then there's a, as I mentioned, zone files in two ways. There's another, which I call immutable storage, and that actually contains, the URI, name, URI, public key, and the hash of the data of the file. And so you can basically verify, is this indeed the latest version of the file? Because in this scheme, you get to update, X can update the file, but it's hard to tell for user 2 whether that is actually the latest version. The paper mentions that you probably want to stick version numbers in it. But if you really want to guarantee to be sort of the latest version for a particular name, if you use immutable storage, then the immutable storage contains the hash of the file, and that uniquely identifies a particular version of that particular file. That does mean, like, if you update, this record, then that only means you update the zone file. So that means you have to republish or recreate a log entry in the Bitcoin chain, mapping, X to a new hash zone file. Okay, so this is sort of the overall picture for the system, and as you can see, particularly like in this to-do list site, the user X can actually update its his or her to-do list without actually having to publish a new record in the Bitcoin chain. In fact, the only thing that really has to be created in the Bitcoin chain is just X's name. And X, of course, might have many other names that are sitting in the zone files, but the system doesn't rely on for every operation on the blockchain, in which it gets us around a lot of these problems of slow writes, low bandwidth, and the limits on the data that can actually appear in a transaction record, because the only data really has to appear in this transaction record is this name plus the hash of the zone file.
Sorry, how again do we find the zone file if we only have the hash?
It's a very good question. We don't really care where it comes from, and so in fact, they call this the routing layer, right? This basically you tell the routing writer, hey, I'm looking for a file that has the following hash, and then the routing layer has to produce that file, and you can check whether you got the right file by recomputing the hash and see if it matches the one that you are asking for. Any other questions about this?
So sorry, just to clarify, operations within this file storage or these zone files is still limited by the underlying blockchain though, right?
Yes and no. What are you thinking?
Or just like, because modifications or changes to like the file would need like a new hash and therefore a new log entry within the blockchain.
Yeah,
so you still have to wait for that to be quote unquote accepted, which is like an hour, right?
Yeah, although absolutely true. So when you make a change to the zone file, that has to run through the TXN. But for example, updating the to-do list wouldn't have to require a Bitcoin transaction. You don't really update the zone file at all. You're just updating the to-do list file, and the zone file only contains the name to do and the URI plus the public key, but you're not updating any of those.
I see, but don't we store also the hash of the file? So if we change the content,
that's in only, okay, there are two cases for the mutable. There's the mutable storage and the immutable storage. And what they propose is that for immutable storage, like storage that you don't update, you can actually stick the hash of the file in there. But for mutable storage, that is going to see a lot of writes. You shouldn't do that. You should use this scheme.
I see. And then how is it possible to validate with mutable storage that you're getting the right data then?
Yeah, so presumably that's a very good question. Well, you can validate whether you actually got data that actually was produced by X, because you have the public key for X, and you can verify whether actually the signature on the to-do file indeed checks out with the public key of X. So you at least know that X has written it. You may not know if it's the most recent version. And so the paper sort of doesn't really talk about this in great detail, but basically says, you probably have to stick version numbers in it. And so at least you can detect rollback. But it's a little bit vague, actually. I don't know how to actually, you can't really ensure that you actually got the latest version.
But so where are the modifications to mutable storage coming into?
Your to-do file lives here, here's my to-do file. And if an application to my to-do list application wants to update to the to-do file, it just goes ahead and does it, and then signs it, using the public key, and sticks it in for the given URI.
And would that be done through the routing layer as well? Because you want to find where in the storage.
Well, yeah. So user 2 will retrieve X's zone file, correct? And once it has X's zone file, it knows where the to-do file is, because there's the URI sits in the zone file. And so again, and then it can retrieve it and check the signature.
About the URI, is it only one URI per name in the zone file, or can you have...
I don't know. Unclear exactly how it works. So I'm not, I didn't check out the source code and look at the specific format of the zone files.
Since we're publishing the public key together with all the rest of the data in the zone file, does it mean I can just make up a private key, make a matching public key, and just stick something in there and say I'm user Z, because I do provide the public key? So can I not just lie?
Well, you can't falsify the zone file, correct? Because the zone file, the hash of the zone file must match the hash that sits in the blockchain. So only the person that actually entered the blockchain record mapping X to that hash zone file, only that person could have produced that zone file.
I see. Thank you.
Okay. Well, so this is basically the big picture, and if you got this as the if you got this part, then basically the rest is sort of details, important but maybe less important. This is the key thing to understand. Okay. There's a couple things I want to go over. In particular, I want to talk a little bit more about name creation, because there's a couple little details that are actually interesting. So it turns out that name creation actually has two parts to it. First of all, the user needs to have, of course, some Bitcoins, because you got to pay. And the reason you have to have some Bitcoins is because you got to convince one of the miners to actually include your transaction in the Bitcoin ledger. And so it turns out there are sort of two transactions for every name that you create. One is basically a pre-order transaction. And in the pre-order transaction, you don't really list the name, but actually the hash of the name. So anybody who sees the pre-order transaction doesn't know what the name is, but does know what the hash of the name is. And then there's the second transaction really registers the name. And that basically contains the actual name for which we first published the hash and the hash of the zone file. And so why is this done in? This is actually something that Namecoin did, and they adopted it from Namecoin. Why do it in this way?
Because if you directly announce the name, then someone else can race you and try to register that name before you.
Yeah, this is sort of a common problem. It's called the front runner problem, correct? Oops, there we go again. Sorry. So the front runner problem is exactly as described. Let's say you're trying to register google.com, and somebody sees you're doing that, and of course you submit it to transaction, correct? It's not in the blockchain yet. For example, a miner might actually see it, or somebody else that actually sits in the Bitcoin network and decides, okay, I'm going to run ahead and trying to get my transaction that claiming google.com into the Bitcoin before you, and then I own google.com. And so to avoid that problem, you first actually have to enter the hash into the Bitcoin chain. Then you wait a while to make sure that that record sits in the Bitcoin blockchain. You have 10 blocks, and then after that, you're sure that you burn the name in the, as they call it, in the blockchain. At that point, you actually do the actual registration of the name.
I got a question regarding that.
Yeah.
So why is it not possible for an attacker to say pre-compute internally the hash of google.com and then look through the blockchain and see if someone posted a hash of Google?
Yeah, absolutely. So presumably, there's a slightly more sophisticated than this, than just purely the hash. There's presumably a bunch of other arguments that go into it, including a nonce or something. Otherwise, you could just make a dictionary, correct? And in some ways, this is like really not their invention, but it is, as I said before, came out of Namecoin. Okay, so let's go back to the sort of collaborative apps or collaborative decentralized applications. So let's just go back to our to-do list as an example, and just to see how it really would work. So sketch out again how that would work. So basically, we have 2 users, correct? Running the to-do list app. Here's U1, here's U2. And they basically exchanged, some information with each other. Basically saying, in some way, U1 has learned about U2's name, and U2 has learned about U1's name. And that is sort of that step, of course, has to happen. It has to happen securely, in the sense that U1 really needs to know that that actually is U2's name. Then they can U1 can U1 can look up U2's name. Get the zone file from that. Like find the entry for, say, the to-do list in the zone file. The zone file also contains, and the public key. And this might be not like, U2 might have many public keys or private keys, because you probably don't want to have like one master private key that you use for everything, because if you use that one master private key or somebody stole it, you're in bad shape. So typically, I think in Blockstack, there's sort of public-private key per application. So the U1 basically has UT's name, looks up the zone file, finds the to-do list, the public key, and the URI. Through the Blockstack file system, which abstracts away the different storage providers, and actually retrieves, the actual name, the actual file, checks the signature on the file, maybe version numbers, and then basically use that to construct, the to-do list from U2 and merge that with U1's. And similarly, basically U2 does exactly the same thing, it has U1's name, and boom, it goes off and retrieves U1's to-do list, and that way they can have a collaborative application. And so, for example, when U2 updates its file, then periodically U1's app goes and retrieves the new the to-do list and just sees if there are any updates. Does that sort of make sense? And you see here, I think this is like one of these central points with decentral applications, is these applications are built in quite a different way than the ones that we talked about very early on, correct? Like if we go back to this picture of the centralized site, like we're building a to-do list application, correct? Like in the database, there would be U1's to-do list and U2's to-do list. And the app, like the to-do list app, basically, retrieves these, the content of these to-do lists with a simple SQL query, and puts them together and actually presents them to the user. And we see that, like in this decentralized scheme, there's quite a bit more mechanism involved to actually make this happen, and the programmer doesn't really have the sort of the same ease of the SQL interface as in the centralized case. And so I think this is one of the sort of maybe the sticking points with these decentralized applications. How can you make them as easy to write as sort of decentralized versions? Okay, so I want to leave some time this time around, instead of doing breakout rooms, maybe just leave some time around time for just questions or discussion. Since this is a little bit more of a sort of thought-provoking type exercise than an exercise in, well, here's a hard technical problem and here's the right solution. Just learn the right solution and then use it. So just love to hear people's opinion or questions about sort of any aspect of these decentralized applications versus centralized, or the particular design for Blockstack or any other issue, and maybe we can debate it together.
Wait, so what's the main difficulty in instead of using like a file system API to use like a relational database?
Well, how do you present a worldwide relational database? I think all these user files, all these files from the different users live in all kinds of different storage providers, and you can't like do whatever. You can't do a select across all the storage providers, right? That'd be crazy. You couldn't also download all the users' data to your computer because that would be too expensive.
What about like a linked data database?
Yeah, so I think this is like, if you're interested in this, I think there's an interesting research direction to sort of pursue, correct? Where you could actually build scalable database infrastructure where users still control their own data, have the different locations, and provide sort of a relational data type interface. Certainly, Blockstack doesn't offer it to you.
I guess another question is, like, what are the benefits of this decentralized PKI versus like a Web of Trust PKI, which I guess is also decentralized?
Yeah, so totally other, just maybe some points here, correct? There's sort of there are other Web of Trust API, Web of Trust PKIs. The one I'm most familiar with is is Keybase. I think which we mentioned a couple times before. Keybase actually, we haven't talked about this in greater detail, but one of the things that's also a challenge in these kinds of systems is like, how do you represent groups of users? Right? We saw that a little bit in the Sunder paper, where you have group names, public keys for the group names, and how to create them and how to manage them, and actually stick them in. How do you incorporate those in the chain of records, name records? And Keybase has a really thought out story for that. Actually, it's a very impressive. It's probably the sort of I probably consider it the sort of the best sort of decentralized PKI out there, and the most thought out and probably most widely used.
So are there any benefits of doing it of like Blockstack's method, or is it just more extensible?
Well, one of the things that actually Blockstack gets, correct, is this uniqueness properties. Because in the web of trust, there's basically not a global naming system. It is like my to-do list or my contact list, and whatever who I name. If I have a name John for some particular public key, that is my John. And if I send John to you, it's like the text string John probably resolves differently in your contact list than in mine. And so in fact, so Keybase is much more is decentralized, but it doesn't really go for these sort of global unique names. Now it is the case that Keybase once in a while publishes the hash of all the names of the complete Merkle tree of all names in the blockchain too, so that you can sort of verify whether Keybase actually is not playing in games. But it's a much more, it doesn't really have global unique names.
Sorry, just a clarification question. Earlier on in the lecture, you mentioned how users have basically they can choose who to show their data to,
yeah.
Or who they give access to their data to. Yeah. But I'm not quite sure I see how that's implemented within that system.
Yeah, one way to do it, and I don't know exactly what the Blockstack does, is that you encrypt the same data for different users. So I think if you want to share your data only with user 1 and user 2, then you encrypt it with the public keys of user 1 and user 2, and then those are the only two that can decrypt it. And so that gives you sort of extra control lists.
I see. So you'd have to, for each person you wanted to give the data to, you'd have to encrypt it with like their public key.
Yeah. And you can get more sophisticated about this. You can actually have group keys and give a group of users access to have a lockbox that has a group key in it, and you encrypt the lockbox with the different users, public keys, and then they get access to that lockbox. They get the key out of it, and then they can decrypt the key, so that you only have to encrypt the data only once instead of multiple times, and you only have to encrypt the lockbox multiple times.
Thank you.
That would be done at the level of the content of this zone file, right?
Yeah, presumably. Or maybe the key that is in the zone files will the key for the lockbox, if you will. And again, I'm not actually 100% sure exactly how Blockstack actually the Blockstack file system does action control, whether it does it all. But other people have done these kinds of designs.
Do you think systems like this be able to compete with like this centralized model in terms of performance or scalability? And what would it take?
I don't know. These are good questions. I don't really know the answer. It is the case, correct? Like even the centralized side is not that easy to scale. We've written quite a number of papers, correct, to sort of see how to make them scalable to millions of users. And so, getting anything to a large number of users is not easy. Certainly in the case of the decentralized apps, it's not going to be easy either. But on the other hand, like if there's not byte sharing, like user one actually only have to share to-do list with 10 other users, that should probably not be a big issue, right? Some ways you can think about the decentralized architecture is basically sharded by user. And each app, runs on one of users' computers. So like you don't need like data centers of caches. So I don't know what the answer to that question actually is. I will not be able to give you a definite answer. It's clearly the case that people have demonstrated bigger scalability with sort of these centralized designs, at least so far we've seen, than in the decentralized ones. But one reason of that, of course, is that the centralized designs are like the widely used and most popular, the most deployed cases. I think to me, the decentralized design is just an intriguing design, and that if it could make to be work, that would be pretty cool. Any other thoughts that people might have or would like to argue about?
I still feel like the storage aspect is like the thing that William Luo was pointing out, where like you maybe have an immutable file that's the user information, but the mutable file that you have somewhere else is like a huge problem. In so much that like I don't really understand how you can assure redundancy for the large amount of mutable storage that you might have.
Yeah, I think the answer to redundancy may be not that tough. I think just the user is responsible for redundancy. So if you're like your to-do list, you own a to-do list file, and it's your job to replicate it, multiple times. The Blockstack storage servers do that for you, but you got to arrange, basically for space at the different storage providers to do that. And so I think in the paper they talk about like, oh, you replicated that maybe at Google Drive and at S3. And presumably S3 internally does its own replication, correct? So hopefully, maybe you just actually store it only at S3, and that should be pretty reliable. Probably more reliable than storing data on your SSD on your laptop. And the zone files are small, so they're just widely replicated, and you don't have to trust the storage provider. Any other thoughts?
I was thinking it's a little bit wasteful that you have, in order to register a name and to use this name system, you have to pay. Yeah, so I was thinking, obviously in a blockchain-based system, you have to incentivize the miners, but I was thinking maybe there's a different, cheaper way. I don't know.
Yeah, I'm not sure. It seems in some ways, that sort of the currency and this are very coupled. So exactly for the reason you mentioned, because you got to have miners and you have to incentivize them. Now, I think in general, like with these transactions, they're pretty cheap. Basically you have to just pay enough, correct, that the miner is actually willing to do the include your transaction. And today you also pay for, if you want to register a name in DNS, you actually pay quite a bit of money. Not free. Oh, I don't know exactly how the economics would work out, but it's not obviously clear that this is actually a much more expensive way of doing it, other than maybe you're burning the planet with electricity, at least in the Bitcoin case. But maybe you should use one of these stake of work ledgers instead of the proof of stake instead of these proof of work ledgers.
It will be possible just to swap it out in place of layer 1.
Yeah, I think this is what the paper's arguing, correct? Like their particular design is really not very dependent on the underlying blockchain, and they could easily switch to another blockchain. In fact, this is the second blockchain they worked on, correct? They first used Namecoin, and then they switched to Bitcoin. And I think the argument in the paper is making we could actually switch to another blockchain if we wanted to.
What in particular is stored in the name history?
In the sorry, what's the question, William?
Oh, sorry, the name history in the Blockstack database.
Yeah, yeah, I don't really mean like these 3 different guys. I think
Yeah,
different version of the zone file.
oh, so they're just like version numbers?
Yeah, I think so. I'm not 100% sure, but like these correspond to the free updates to the zone file, correct? Here's number 1, here's number 2. And maybe they keep recent versions of the zone file around. Any other topics that people want to bring up? Okay, so we're in sort of the end of election time anyway. Okay, so let's why don't we stop here? So people that need to leave can leave, and I'll see hopefully everybody on Thursday. We're going to see 8. We had 8 projects, and so the 8 teams will present on Thursday what they've done instead of lab 4, and it should be. And the projects are quite cool and interesting. So hopefully you'll be entertained. And that makes concludes this lecture. Hopefully, there's a bit of the goal is a little bit be thought provoking, and sort of talk about designs, decentralized designs that has this nice property that the users own their data, and and we looked in the context of Blockstack at least one particular design, how they did naming in a way that gives global names, unique names, and human readable names. Okay. So that's the end of this lecture, and then hopefully we'll see you on Thursday, which is going to be our final class meeting. And if you have any questions, please feel free to stick around and we can talk.
Professor Cash, for the presentation, are we supposed to do something like more of a demo, or should we have like slides prepared, or a combination of both?
Yeah, we posted some instructions in the Piazza. You're pretty free to do so. What you want to do, the thing you want to do is convince the class and us, what project you did and why it's cool. So demo is a good idea. On the other hand, you don't have a ton of time. So I think the typical thing to do is people have a few slides for explaining what they did, and then maybe a quick demo to see how it actually materialized.
Great. Okay.
Yeah.
Thanks.
Yeah, and we don't expect you to spend hours preparing for this, correct? It's usually trying to share what you've done.
Okay. Thank you.
Thanks.
I just wanted to ask, so it's like, what is the reasoning behind just using the same Bitcoin, like the blockchain, and just putting the transactions for the naming on there together with all the rest of the things, right?
Yeah, I think the papers. So they started out not doing that. Right? They started out building on top of Namecoin, which is a special purpose ledger for naming, and they discovered basically that there's sort of all kinds of security issues with Namecoin, and one of them being that actually there are not that many miners, and so They observed that basically their miner pools that basically had more than 50% of the capacity and work capacity, and therefore could do anything they wanted to do to the, in principle, to the ledger. And so they wanted to sit on a blockchain that is widely used, very popular, and not easy to overtake by the adversary.
Okay, I remember the 51%. Yeah, I remember.
Yep.
From the, okay, that makes sense. And I also wanted to ask about the URIs. They are URIs to the zone file storage system. They're not just like S3 something something, right?
Yeah, it could be. The problem is something a little bit more general because it's actually interpreted by the Blockstack file system. The Blockstack file system has backends for the different storage provider, whether it's S3 or Google Drive or whatever. And so there's some naming scheme that the Blockstack file system can interpret and then figure out like how to retrieve the right file from the correct backend.
This is just to make them the same.
Yeah, exactly. Because like an application writer doesn't want to care, correct, whether it's stored at S3 or Google Drive. They shouldn't be aware. They shouldn't have to deal with that.
All right.
Exactly.
Thank you so much.
You're welcome.
I had a question about why Zuko's triangle is kind of like a thing that people think about a lot. Like it seems like if you can have like a client side, like interpret the human non-meaningful data, that you can make kind of all the data human meaningful, like on the client side to the user. And so I wasn't completely sure like what the innovation here is, or why why this is necessarily like a trade-off.
Yeah. Well, I guess this is the best slide I can give you, where I can give you a whole bunch of naming examples that basically have 2 out of 3, but not all 3. And sort of example, like we talked about Keybase, correct? There's decentralized, human readable, but not unique. And now you're going to argue whether it's that important to have global unique names. Because whatever, you have some global unique name like 86824, what does it mean? And who's associated with it? So if you're coming from that angle, I think that's a very valid question.
So one of the things that has always kind of bothered me when we're reading through these blockchain type of papers is like what happens in 100 years when the ledger gets to like multiple I don't know if like to multiple terabytes or something.
Mm-hmm. Yeah.
Do we just like do we not have an escape plan? Like what's going to happen then?
I don't know. Hard to speculate 100 years out into the future. I presume what you could do is like put a checkpoint in the. I can imagine multiple schemes, correct, getting out of this. One, you could make a checkpoint of the state, build on the ledger and include the hash of that checkpoint into the ledger. And then as long as you can and replicate the checkpoint widely, and then you can basically start running from the checkpoint and cut out the beginning. This is like not unlike what we're doing in lab, what Draft is doing, correct?
Would the party that does that have to be trusted, or?
Well, presumably the clients want to have to go along, and you realize that they should get that checkpoint to be able to construct the current state of the world. So I presume that would require some protocol change and presumably some fork. And now, this is not a huge issue, correct? At least with the rate of Bitcoin, because the number of transactions per second you can do is actually small. And like if you remember from the Bitcoin paper, there's some calculation like what the total size would be if you do this. Furthermore, if you remember correctly from the Bitcoin paper, there's a bunch of optimizations, right, where you don't really have to remember every transaction for every coin. You basically have to remember the last transaction for every coin. And you could do that by just remembering the block headers instead of the complete block. So Bitcoin has sort of a built-in solution to this problem.
I see. So the main bottleneck is more or less when new machines come up, they need to verify the entire
Yeah.
chain. But
Yeah.
after that,
Yeah.
then things are relatively more optimized.
Yeah, exactly.
Thank you.
Okay, is that it for today? Thank you all. See you Thursday.